Okay, so let me briefly summarize what we did last time. So so yesterday we went through the first binary black hole detections, summary of what was done in O1 and O2. And then we talked about the continuous wave sources. So we talked about the basic physical model, and then we talked about the accreting neutron stars. So I want to finish off, first I want to wrap up that discussion, and there's just one piece left in that, which is what I'll call directed searches. So again, just like Scorpius X1, these are searches with known sky positions but unknown frequencies and spin downs. And in this case, one example of Scorpius X1, but now you can also look at neutron stars which are not in binaries, but just places that we expect neutron stars to be. And excellent candidates are supernova remnants. And so what we want to do is select sources which are either young or very close, or young and close, even better. And so then you have to go through the catalog of possible supernova remnants and look at the best candidates that you have. There's a whole process for that, which I won't discuss here. But as a result of that, you find 3 candidates which are particularly interesting, which I'll discuss results from that for now. And all of these searches are also limited computationally, and they use a project known as Einstein at Home. So this is just like SETI at home. So you can help us analyze this data as well. So you have to go to just Google Einstein at Home. You go to a web page, and you can download the software. You can download a little piece of the data. You can do the analysis, and then you can send us back the results. And many people do this. And before this project started, like 10 some years ago, why would people want to do this? And but it turns out they do, and they do it because they get something called credits, which are just a word for how much time you spend doing computing, and people actually fight for credits, how many you want. If your computers want to make a detection, and which in fact Einstein at Home has been used to make detections, not for gravitational waves so far, but for pulsars, gamma ray pulsars and radio pulsars, and hopefully we'll also make a gravity wave detection from Einstein at Home, then I think you'll get a t-shirt signed by somebody. So anyway. But it's a huge help, and it's an easy way for you to participate in gravitational wave searches. So one of the nice sources that I'll talk about is called Cassiopeia A. So it's a supernova remnant about 3 kiloparsecs away, and it's 300 years old. So it's the youngest one. But this is the list of the 3 that were targeted in this case. So there's Cassiopeia A. But the most interesting one is actually Vela Junior. And there's one more which doesn't have a short name, so it's just G347.3-05. You don't have to care about what it is. This tells you the distance to the source, and this is its age as far as we can tell. And there's uncertainties for Vela Junior, so it's either close and young, or it's far and somewhat old. That is simply the geometry of the expanding nebula from that. So optimistically, we would like this to be close and young. But again, that's something that we'll know later. So the search I'll present is from O1, and this is a reasonably sophisticated hierarchical search. By that, what I mean is that this is limited computationally, so it means that in the first cut to the data, you cannot do the best possible search, the most sensitive search. So instead, you do this in different stages. In this particular case, it is what is called a semi-coherent search, and by that I mean that you can't filter the data coherently for the full duration. You break it up into shorter segments. Each segment you do coherently, and then you combine the different segments in a particular way. And the other thing I should say is that for such things for which you know the age, you can also get an indirect limit on the amplitude, just like the spin down limit. And this is based just on the age, which sets a limit then on the spin down and the frequency of the system. So even in this case, there's some rough estimate for what the amplitude that you expect should be. So the goal is to beat that and beat that by a lot. So this is the result. I won't give you the detail. I'll just present the results at this point. So these are the 3 sources. And the y-axis is exactly this quantity h0 that I talked about last time. So it's limits on that. And so these are the results of these searches. So for each of these, you see it's like 10 to the minus 25 in H naught. And the same thing here. And these are the best current results on any of these searches. The previous results here are the ones published by the Lago-Virgo collaboration, so this beats that by quite a big margin in this case. And again, this dotted line, the dashed line, is the indirect limit. So in this case, it's beaten really handily. So in this case, I have to say the indirect limit is not as significant as even the spin down limit, but still, it's at least something that you have to go on. All right, and the frequency range is, of course, going from pretty low frequency up to more than up to about 1.5 kilohertz. And if you want to convert this to a limit on the ellipticity, assuming that if a neutron star is there and it's emitting because of these mountains, then this is the corresponding limit on the ellipticity. And here you show results for Cas A, this other supernova remnant, and your Vela Junior in the two cases, the young and the close, or the far and the old. So the best one, of course, is the young and the close, and that is the one for which we get the best limit on this ellipticity. So this is comfortably in ranges where, you know, if you say that you found something, neutron star with this ellipticity, nobody would be surprised at all. So this is astrophysically interesting. So you're ruling out sort of astrophysically interesting parameter space even in this case. And this is Cassiopeia A, that is the green one, that is the worst limit in this case. And Vela Junior, if you assume it's far and old, that gives you then this line here. And you can expect similar results to come out also for from data from O2 and so on. Okay, so let's move on. So I talked about this also the all sky searches, so I won't discuss that here in the interest of time. So let me just move on to the next step. So let me now, so next step is now going to the data analysis problem. So, and this involves statistics. And as most physicists, you don't really want to learn statistics. And this is sort of, if you do engineering, then of course, electrical engineering, then this is an important part of it. But in general, as a theoretical physicist, this is not something that you really want to spend your time doing. So I did my undergraduate study electrical engineering, and I said, no, this I don't like. I want to do physics. And then after that, I ended up doing again the same thing which I had left. But anyway, it's actually fun. And even before that, I need to describe very briefly at least how a detector responds to a gravitational wave. Scott's going to talk in more detail about this. I'll just mention here briefly in a couple of slides the basic concepts. So imagine now gravitational wave traveling along the z-axis. So assume it's a plus polarization. So then the space-time metric is then of this form. So it's the xx and the yy piece have an h plus here. If they were the other polarization, you would have a dx dy piece, which would be the h cross, the cross term. And of course, you can do, from this, you can look at this, and you can say that if I compute the proper length in the x direction and the proper length in the y direction, the x direction is stretched, and this one is squeezed if h plus is positive. And then roughly then what you want to measure is that in such a configuration that you'll hear a lot about in lectures by Nergis tomorrow, you have an interferometer in which you have x and y arms, and you want the differential arm length in these two directions. And what you want to measure is the delta L, the change in differential arm length divided by L, so that is h of t. You got to be a bit careful about how you interpret this kind of a calculation. It's not the right calculation, in fact. So the first thing is that a spatial separation is not really something that you directly measure. So what you measure are the phase differences of photons that go from here and come back versus the ones that go here and then come back. So what you actually want to compute is the phase difference of a photon, or change the phase of a photon as it travels in this metric here. And in fact, that can be done, and this is sort of the right calculation. So look at the more general case now. So look at a metric now which is of this form, and this h plus and h cross are sort of are waves. So they are functions of only t minus z. And you can just stare at this, and you can figure out that this metric has three symmetries. So first of all, nothing depends on x, so that's a symmetry. Nothing depends on y, that's a symmetry. And nothing depends on t plus z, so this is also a symmetry. So you have three conserved quantities, And what you can do if you want to look at light, which travels along null geodesics, so you have 3 conserved quantities that you get just by this very simple analysis. And you can, this is now exactly like the redshift calculation in the cosmology. So again, you have, or in Schwarzschild spacetime. So again, you have a killing vector and you have conserved quantities. So that gives a redshift in a Schwarzschild in a black hole spacetime. So exactly the same calculation. And what you want to do is you want to use photons to measure the arm lengths. And the actual measurement is the phase difference of the photon along the 2 arms. So to set up this calculation, what you do is you get some point from which you emit photons and the other point where you receive photons. Then you work in a transverse traceless gate so that these points, coordinate locations of these points O and P are fixed. You shoot a photon from here with some direction cosines and it reaches here P. And what you want to do is you want to find the Doppler shift of this photon as it goes from here to here. Okay? And the same calculation works for LISA, same one works for pulsar timing arrays, and so on. And it's interesting that the photon doesn't travel a straight line in these coordinates. It's actually lensed by the gravitational wave as the gravitational wave goes on. So if you shoot a photon here with these direction cosines alpha and gamma, in fact, when it reaches here, it'll have a slightly different alpha and gamma. And the frequency omega will be changed by some delta omega. And you can compute these small changes to linear order in H plus and H cross. And this is a very sort of nice paper, I think, by Esterbrook and Wahlquist, which I think deserves to be read much more widely than it perhaps is. And the result of this is very nice. So it tells you that the frequency change of the photon depends only on the starting and on the end point. So it tells you that delta nu by nu is given by this expression here, which looks a bit complicated, but really it is quite simple. If you just stare at this for a minute, what you get is an expression of this kind. What you get is, these x's are the unit vectors in the different directions. K is a wave vector. And then what you get is an expression of this form. And for the ground-based detectors, it simplifies even further. It turns out that what you care about is the case of the long wavelength limit, in which case the wavelength of the gravitational wave is much larger than the arm length. And in this case, you get a very nice expression at the end after integrating this out to go from the frequency shift to the phase shift. So these are the unit vectors along the x and the y arms, and what you get is the phase shift is given by this expression that you have seen before, I would guess, at some point. This is the same as the other simple calculation, but that's an accident, so this is the right calculation to do here. So what you get is that the thing that you want to compute depends linearly on h, that's no surprise, but it is multiplied by this quantity called the detector tensor. So it's again the obvious tensor you might construct from this from an L-shaped detector. So xx minus yy. You contract that with h, and the result is then the phase shift. So now let's go to the gravitational wave themselves. So now you work in the frame of the gravitational wave that's coming towards the detector. And then the important thing is that you can choose a frame such that the H plus and H cross can be written in this form. This is just like choosing the principal axes of, let's say, an electromagnetic wave. So you can always choose an x and a y frame so that the electric and magnetic fields are, the components are 90 degrees in phase away from each other. Okay? And in this case, you have a part of the amplitude that's slowly varying. That's what I call eta of t here. And you have some a plus and a cross that the ratio of those determine whether it's linearly polarized, circularly polarized, or elliptically polarized. This quantity eta of t is, for a binary system, this is slow increase in amplitude as you go close to the merger. For the continuous waves, this is a constant. Okay? So in fact, from this analysis, you can treat any of these model searches, by which I mean searches for which you know what the expected waveform is, in this language here. So this covers both binary spirals, neutron star, black hole binaries, and what have you, and also continuous waves. Okay? The difference in the two comes in the next step. So now when you go from this H plus and H cross to what the detector will see, that is this combination of H plus and H cross. So of course we saw here previously that this delta phi is a linear operator acting on this H. So it must be a linear combination of H plus and H cross, right? That's obvious. And then you have two functions, F plus and F cross. It's also obvious that F plus and F cross will depend on the sky location, right? So if I have an L-shaped detector, it's, as Scott explained yesterday, is the most sensitive if the source is on top or on the bottom, and least sensitive if it's on the plane. And in particular directions, you get zeros, in fact. There's also one more angle here, which again Scott described yesterday. It's called a polarization angle. And this is sort of telling you about the frame of this wave frame, which is this principal axis for this polarization, in relation to the frame you set up for the detector itself. Okay. So that's then one more angle. So in the end, F plus and F cross depend upon three angles. The two angles contained in sky location, and the extra angle contained in this side. And if you think about it, this is not surprising at all. So what you have here is a relation between two orthogonal frames. So you have a frame which is connected to the wave, so that's so imagine it's some x, y, and z frame for the wave that's coming, and then you have the detector, which is again is some arms, and then you have some, let's call it little x, little y, and little z. So and what you want to do is you want to find the transformation to go from this frame to this frame. And at the end of the day, this is just what you might have learned as the Euler angles in, let's say, classical mechanics. So there's three angles again for the Euler angles, and those are related then to the sky location, that is the direction from here to here, and the rotation and the orientation of this axis here. Okay? So that's why this F plus and F cross depend upon three angles and not two. And this is where one difference comes in between the property of the signal. If a signal is very short, this F plus and F cross are essentially constants. So because the detector is not going to move really significantly over a scale of, let's say, 1 second, but if I have a continuous wave which lasts for several weeks or months, then of course these will be functions of time themselves. So I'm not going to go through this polarization angle in any detail. I'll just assume that that part is now clear. Okay, so now we have then understood how a detector responds to a gravitational wave, and we also understood how to write the wave, the H plus and H cross, in a convenient way. So now we go to the actual heart of the problem, which is the problem of detecting any of these signals. And before that, we will do an even simpler case, but let me just set up the problem here. So the general problem is the following. So we have some detector output, let me call it x of t. So this is what is measured from, this is not just gravitational waves, it could be it could be a microphone, it could be anything, okay? So you have some measurement x of t, which contains a noise, let's say n of t, and possibly a signal h, which depends on t, but also on some signal parameters, let's call them mu in this case. So this mu could be the masses of the binary system, the spins, could be the ellipticity in the case of the continuous waves, could be its frequency, and so on and so forth. Okay? So the goal of the whole problem is to first determine whether there is a signal or not, like a yes or no question, and then if there is one, what are the best fit parameters for mu, and what are the error bars on mu. Okay? So that is a general problem that you want to solve. And assume for the moment that we know the distribution of the noise. So I'll explain in a bit more detail what that means. But assume that you know the statistical properties of the noise. So that means in this case that if you sample this x and this x of t at some discrete time intervals, you get some samples of the noise at these discrete time intervals. Assume that you know what the distribution is of the noise. Then, given that the distribute for the data is also easy to get, because if you do x minus n, if you do x minus h, you get the noise, right? So the distribution of the data given the signal is the same as the distribution of x minus h given noise. Okay? So this is the first thing to keep in mind. So now let's go to an even more simpler problem. Okay? So this is what is called as hypothesis testing. So the simple problem now, the classic one which you might find in textbook is, let's say you toss a coin and you don't know if the coin is biased or not. And you want to say, is the coin biased, is it not biased? So you toss the coin, you get heads some n number of times, tails some m number of times. And from that you have to make a decision whether the coin is biased or not. So a problem like this, right? So you have two hypotheses. So you have, let's call them H0 and H1. And you have some quantity that you measure, let's call it X. And also now say that you know the distributions of X under both of these hypotheses. So this is the analog of what I said here. So in this case, the hypotheses are that this H is present or H is not present. And also in this case, you assume that you can compute in some way, which I'll describe in some detail later, what the distributions are of X with the noise and without them, with the data and without the data. So then the question is simply, given an observation of X, how should we choose between H0 and H1? So if you phrase it a bit more generally, so you'll see, you can think of it in the following way. Let's say this is the space of all your possible observation. Let's comment a big X here. So then what you want to say, so you get a measurement, you get some point in this X. You could get something here or something here. In each of these cases, what should you do? How should you choose X0? How should you choose between the H0 and H1? So what you want to do is you want to divide this space into two regions, such that if the observation lies in this region, you choose, let's say, H0. If it lies in this region, you choose H1. The question is, how do you break up this observation space into these two different regions? And this is one of these things that were done by people in the early 1900s. So they were looking at, I think they were genetics or things like that. But anyway, so the result is based on two quantities that you have to compute. The first is a false alarm probability. So that means that, right, so let's say that the region, yes, let me set it up. So let's say I want to find the region C. So this is in the region C, such that, so if the data happens to lie here, then you choose H0, otherwise you choose X. This is then X minus C, otherwise you choose H1. So if you want to become famous, of course you want to find gravitational waves, win a Nobel Prize, then you want your result to be here, otherwise you get here and you stay at home and try harder. So the first thing you want to control is the false alarm probability. So you don't want to make a claim that you saw something and plan your trip to Stockholm and then find out later that you got nothing, right? So you want to sort of control that in some way. So that's the false alarm probability. So it's a probability that you are in the region X minus C, but in fact, the hypothesis H0 is true, so you got to use a probability distribution P0 of X. So that's your false alarm probability. Okay. False dismissal probability is the other way around. So you want to say you sort of missed a signal, right? So you could have gone to Stockholm, but then you ended up not going because you just had bad luck. So that is the case in which H1 is true, but you end up in the region C. So that's your false dismissal probability. So the fundamental result is the following. Given these distributions, the best way to choose this region C is the following. You look at the ratio P1 upon P0. You get this function lambda of X based on that ratio. It's called likelihood ratio. Then given an observation, you get a value for this lambda. You choose a threshold on lambda for a given choice of the false alarm probability. So you say that, well, I can allow myself a 10% chance that I book my trip to Stockholm and I actually don't find anything. You cannot make it zero, right? I mean, this is statistics, so you cannot make, you got to choose something for that number. So you choose some value for alpha. Could be 1% if you're or 0.001% if you're really conservative, right? It's up to you. You can choose what you want for alpha. That gives you threshold for lambda. Or rather, given this lambda, right, a value for a threshold will split your parameter space into two regions, and you want to compute the false alarm probability based on that, on the threshold. Okay, so that's the first step. And then, for a given observation, then you choose H1 if you exceed the threshold, and you choose, let's say there's the bad luck case, if lambda is below the threshold. And the result is that this is the optimal way to do it. So this is the way for which you minimize your false dismissal probability for a given false alarm probability. Right? So you want to make this to be as small as possible, and you want to fix a value for this. Okay, is that clear? Any questions at this point? Yeah. This is a choice that you have to make. So this is up to you, really. I mean, so so typical choices are 10% or 1% or something like that. So, but you have to make a choice for that. At least in this set. But anyway, you always have to make some choice. Right? No matter what you do, it's a statistical thing. So there is always a chance that you will be wrong. You just have to make sure you understand how wrong you can be possibly. So these are like the known unknowns, if you want it. Okay. So this was shown by these people, Neyman and Pearson, back in the early 1900s, and this is still a very useful thing to do. So the problem is the following, though. So in our case, we don't have just two hypotheses. So imagine if you have the amplitude for the gravitational wave signal, it's not a discrete thing, right? It's not 0 or 1. It could be anything from 0 to some it's a continuous variable. Right? So in this case, in fact, there is this result that I said doesn't actually go through it. It's not actually true. But still, you say that the best choice for this hypothesis is you have then different hypotheses. Let's assume the discrete case in which you have some n different possible discrete alternatives. Okay? So in this case, then what you do is you compute these different likelihood ratios, pi upon p0, for each of these hypotheses. And then for each of them, then you choose the lambda I, which is the largest. So that is the most likely one. And then you can then extend this to the continuous case. So you have some continuous parameter which we call mu here. So then you compute this ratio, the likelihood ratio of p of x given mu, divided by the case when you have no signal. Okay? And then the procedure is clear. So if you know the distributions, then you just want to compute this function, and you want to see at what value for mu you get the largest value for lambda. And that is your best fit value for mu. And you can extend this to get the error bars on mu as well. Okay, so this the best fit value for mu, that is the maximum likelihood estimator. And then you can also, with a further little bit of more work, you can also get error bars on this parameter. So the goal then is to simply compute this likelihood ratio for the case of the gravitational wave, and then see how significant is the best fit value. Does it exceed your threshold? If yes, then you can go to Stockholm. If not, then you stay at home. Of course, I'm simplifying, but that's essentially that's right. Okay, so now let's go. So now we discussed at least the frequentist aspect of this. And of course, I should also say here that there's two different camps in statistics. So one is called the frequentist. This is what I described just here. And the other is called the Bayesian, which I'll talk about a bit more probably in the next lecture or later in this one. So they have a very different viewpoint, but in the end, this is still a very important function. You still want to always compute the likelihood ratio defined in this way. How you interpret that and what you do further with that to get the best fit values and the error bars, that is different, but still, this is the key thing that you want to compute. Okay? So let's look at now the noise itself. So I told you that we want to understand the noise distribution. Well, what is it? So let's do this slowly again. So we have a time axis, and we have here the noise, and I sample the noise at some discrete times. Okay? So let's assume that we have the noise samples Ni. Okay, the index I it's a discrete one going from start of observation to the end of your observation. So then what you have are the distributions of these Ni's. You can of course look at distribution of each of these N's independently. You can also look at the joint distribution, the 2-point function, if you like, of Ni and Nj. You can look at the 3-point function, the Ni, Nj, and Nk, and you can do as much as you want. Okay? So the first definition is that the noise is stationary if these distributions do not change under shifts in time. In other words, if I look at Ni and Nj, they should be the same. Secondly, if I look at Ni and Nj, if I shift both I and j by the same amount, I should get the same distribution again. And same applies to any of the higher order distributions. And we typically never go beyond the second order, so this is all that you really have to care about. So it really just means that this 2-point function should be the same shifted in time, and the mean or the statistical properties of noise should be the same at all times. The easiest definition, the actual data does not actually follow this, so I'll describe again how we deal with that, but at least a simplifying assumption just to understand what's going on, let's go with this assumption for the moment. So the other thing to keep in mind is that it's not true, even with this simplified assumption, that the different noise samples are independent. They're not. So this distribution here, Ni and j, is not like a delta function. It's not 0 if I and j are different. Okay, so it's not that simplifying an assumption either. So this covers a reasonably large class of noise models. But the important thing is that if I look at the same thing in the frequency domain, with this assumption here, you can show that different frequency bins are uncorrelated. So this is the key thing that simplifies the whole business. Okay? So stationarity means this condition here in the time domain, but in the frequency domain, it means that different frequency bins are uncorrelated. And that's something you can show with a very simple I mean, the actual mathematical proof is complicated, but at least to understand what's going on, you can do this very simple thing. So you do the following. You have the data in the time domain, take its Fourier transform, go to x tilde. So this quantity called the periodogram is simply the power in the noise in the frequency domain divided by the observation time and the limit of large T. So this quantity tells you how much noise there is in a given frequency or a given frequency band. So the first thing, what are units of S? So assume X is dimensionless. This is a time, there's a dt here, so that's seconds. So X tilde is in seconds. The square is in second square divided by seconds, so the whole thing is in seconds. That's inverse of a hertz. So it's a density in the sense that its goal in life is if you multiply this by some frequency range and you integrate, you get the noise in that frequency range. N is the noise, so N, so the N is just a noise, and the tilde means a Fourier transform. Okay, so take the noise and apply this operation, again for the discrete case, so that is your N tilde. Okay. So the key thing here is that this quantity Sn integrate in some frequency range gives you the noise in that frequency range. So if you take sort of spectrum that Scott showed the other day, if you integrate that for the whole frequency range from 0 up to the largest possible frequency, you'll get a large number. Well, large in the, it's not going to, if you convert this to a sort of a strain, it's not going to be sort of in the sub-nuclear size thing. It's in a smaller frequency range, and that's in the part where this noise curve is small, that you get this high sensitivity. Okay? And this quantity here, this Sn, is the thing that tells you how that goes. So in the interest of time, I'm going to skip further details here. I just want to give you this flash this definition here for you. So I told you that different frequency bins are uncorrelated. So it means that if I take the noise at a given f and take the noise, its complex conjugate at an f prime, and take the expectation value, what you get is a delta function. And the thing that goes before the delta function is precisely this spectrum that we computed. So this is something you can show just by looking at Fourier transforms. I won't go through that here. This is an exercise for you if you want. But it's quite easy to do. And so this is a different definition of this power spectral density. And again, as I said, the integral of this S over some frequency range is the power of in that frequency interval f1 to f2. So it's a density, which means its purpose is to be integrated, and then you get something that's the invariant thing. So integral of S are the important things. Okay. All right, so there's complicated, not complicated, but at least some techniques to estimate the spectrum. Again, I probably should not go through the details here. Let's see. Yeah, let's skip that. So I think I'll just mention here the things that you got to deal with, right? So what you have to do, you got to do two things. First is you want to get estimates for the spectrum which have a small variance, so which don't have large error bars. That's obvious, okay? And the second thing is that you just have one data stream, X. You do not know whether it has signal or not a signal, right? So your estimate of the spectrum should not contain the signal. Okay? So what you want to do is you want to make sure that your distribution for the noise, what you compute from computing the spectrum, is unbiased by a signal that could be present. Okay? So I won't go into the details here. I can see that many of you are not, this is not the most exciting part of lecture, shall we say? But still, it's something that you really have to do. Okay? So this is something, it's actually fun once you get into the details of it, but this is something, I won't go into the further details at this point. Okay? But there's one thing I do want to tell you, and which again is one of those things that physicists may not always learn, but this is the most important algorithm ever invented in the history of computing. And this was in 1965, I believe, by people called Tukey and Cooley. And in fact, Gauss also had a version of this back in the 1800s. But anyway, the goal of this is to compute the Fourier transform. So remember from what I said, if you have a stationary noise, then it becomes simple in the frequency domain. So we want a simple way to do Fourier transforms. I may say, well, Fourier transform, that's easy, right? I mean, I just take my samples X. In the discrete case, I have these phases. I multiply this and get the result, and that's it. Couldn't be easier, right? But if we did this in brute force, none of the analysis I talked about could be possible. Okay? So almost all of signal processing could not be possible if you simply did this by brute force. Why? Let's do this slowly, right? So we want to compute this x tilde for different frequency bins. That's labeled by this integer k. So for each k, I got to do this sum of n things. So that means for each k, I need to compute n of these sums. So if you just think about it, it implies the number of operations you got to do is of the order of n squared. So if n increases, then it blows up at a particular point, right? And numerically, you just couldn't do this with the amount of data that we have. So just for the analysis here, let's take n to be a power of 2, just for simplicity. Okay, so 2, 4, 8, 16, and so on. So the actual data we get from LIGO is sampled about 16 kilohertz. So that tells you how many samples you have in each second. Okay? Of course, you downsample that, but still you get thousands of samples each second, at least. So even if you have like a few hours of data, that is, that's a lot of time samples. So then what do? So you look at this sum, and you split that into the even and the odd parts. So you get two things. First is the sum of all the cases when this index is even, and the ones where it is odd. Again, you say, well, how does it help? Just split this into two pieces. We still have to compute each piece, don't we? Well, yes, we do. But the important thing is that given this even and the odd thing, you can reconstruct your final output. Okay. But the important thing now is the following. To compute this is order n squared, of course, but n by 2 squared because you just have half as many terms here. So you get n by 2 squared, and you got to have both of these. So the number of operations you have to do, if you do it this way, is n squared by 2. So you already gained a factor of 2 in this. And you can go further, right? So you can say I break this up into even and odd pieces after relabeling suitably. And I break this one as well. And you keep on doing till you're just left with 2 at the end. Well, how many times can you do this? If the number of samples is 2 to the n, you can have n layers of this. And that's just the log to the base 2 of the number of samples. Clear? So in the end, by just repeating this process so many times, in each of these iterations you have n operations, of course, but you have only log of n repetitions of that. So then what it means is that you reduced your operation count from order n squared to order of n times the log of n. So this is divide and rule, right? So you have a problem, big problem, break it up into smaller pieces, smaller pieces, smaller pieces, and at the end you get a simple problem that is much more easier than the full big problem. So, and this is a huge, huge impact here. Okay? So if you have, for example, n is 2 to the 14, ratio of n to log of n to the base 2 is about 10 to the 3. And there's extensions of this algorithm which also work, and it's not a power of 2 by this suitable breaking down the problem into smaller pieces. But the point now is that you reduce the order from n squared to n log n, and this is huge. Okay? So it's not exaggeration. This really is the most important numerical algorithm I think ever invented in signal processing. So let's apply all of this to the case, the simplest possible case, right? So the case when the signal is purely sinusoidal. So we now slowly build it up and now go to the detection problem. So let's start with the simplest possible case. So signal is some amplitude times cosine of a phase, which is omega t plus an initial phase. So the question is, what do we do to the data to say whether h is present or not? And how do we estimate its parameters? So again, you have some time samples, call them T1 to Tn, let's say equally spaced, with some spacing delta t. So again, we have two hypotheses. We have either x is just noise, or x is noise plus a signal. And once again, you compute this likelihood ratio. So this x minus h and n of x. And then assume the noise is Gaussian. So what that means is that the noise itself is this multivariate Gaussian. So I have n of these samples. So the noise distribution is some matrix here multiplying ni and nj, and the exponential of that. And once again, I do not assume that the C is diagonal. So it means that different noise samples can be correlated. But in the frequency domain, which is where things simplify, different frequency bins are independent. So this whole expression in the frequency domain can be written as sum over different frequencies. And this now, once again, is a calculation that you can do. It's not completely trivial, so it's got a little bit of work to do. But you can show that this quantity here is exactly this quantity here. So to compute the noise distribution, of course, it depends on the spectral density, but in a strange way, it depends on the inverse of the spectral density. So it's the noise squared divided by the spectral density. Okay. So then you define what is called the inner product between any two signals. So you just use this expression here, and you have a signal G, a signal H. Its inner product is this quantity here. So the important point is that the inverse of the noise spectral density here. So when the noise is small, so that contributes more to the integral. So the regions in frequency for which you have low noise contribute the most to this inner product. So now we can finally now go back to our likelihood ratio. So we have again the ratio of two of these Gaussians with these inner products in them. So lambda is exponential of this guy divided by this, then without the h. And then a short set of manipulations, what you then do is that log of this lambda is given by this combination here is x dot h minus 1/2 of h dot h. So we just applied the procedure that I described to this very simple case, and we ended up with this expression here. So now we take this simple signal model, this A sine of this phase and initial phase, and we want to estimate the phase, the frequency, and the amplitude. So we want to find the point where log of lambda is maximum. So I think it's probably time to take a short break. Is that, if you want? Yeah. Okay, so let's take a 10-minute break, then we continue 10 minutes. Yeah, of course, yes. Questions?
These classification problems, for these classification problems, machine learning algorithms are
Yeah, so there are, in fact, yes, I don't have time to go into describing that for the basics, but yes, that is a big field of research, yes. So there's a bunch of people involved in applying machine learning to these problems, yes. But I bet, I mean, for me, I don't know how successful that will be. I would guess it will be successful, but for me, it is still crucial to compute the likelihood ratio no matter what you do.
These are baselines, right?
Yes, indeed. Oh, you mean how do I estimate the spectrum removing the signal? Yeah, so that's somewhat complicated. So the thing to do is you want to average over the noise in some way, right? You want to average over the different frequency bins or different time samples or whatever. If you do the average and assume that you have noise, 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 big signal and noise, okay? If you do an average, the signal will contribute to that average. But one easy way to fix that is to not do the mean, but the median. So in terms of the median, what it means, I rank the noise in its value from, let's say, the smallest to the largest value, and I take the one that's the 50 percentile of it. So that is insensitive to whether you have a few large outliers or not. So the median is a very simple way, and it's a really practical way to remove the noise effects from that. But there's other ways, but this is the most commonly used one.